Natalis in French, but that's really no problem. Hello everyone, welcome to this brief presentation of my thesis work. I hope that the topic will interest you as much as it interests me. I'm going to put my camera on, that's going to be nicer. Yep, here I go. Sorry for the delay. I think that there are several aspects of its teaching that are problematic in scientific higher education, and I will present here what these problems are and how I plan on tackling them. First of all, a bit of context. What is entropy? Essential notion in thermodynamics, which is a branch of science that studies energy exchanges, as you all know, and which central notions are heat, work, and temperature. The way entropy is usually presented, and which, spoiler, is problematic, is that it's the disorder, the chaos of a system. The more disorder a system has, the more entropy it has. The way I rather choose to present it is like this. Entropy is the spread of energy, or even as engineers would call it, it's a measure of energy quality. Take, for example, the following diagram. At the top you have a hot tank in red, and at the bottom a cold tank in blue. Heat is allowed to flow from the hot to the cold tank via a machine that exploits this temperature gradient to produce useful work. In the end, we end up with two lukewarm tanks in purple. The entropy is greater in the lukewarm system. The energy is more spread there. It is of lower quality in the sense that you can no longer exploit the energy in a machine. Here are also three very important features of entropy. It is specific to a system. We can say that one system has a high entropy and another system has a low entropy, even if they have the same energy. The entropy of the universe system always increases, whatever the process taking place in it. This is called the second law of thermodynamics. And third, this is why we say entropy defines spontaneity. When it increases, it signals a spontaneous process. As I said, entropy teaching has risen many questions in my research. I've chosen the two most important to present here to you. First, the emergence of the macroscopic properties of the microscopic models. We shall see it is not always intuitive, which undermines the metaphor of molecular disorder that we usually use. Indeed, this metaphor can be sometimes useful in some carefully chosen cases. For example, to explain the entropies of the states of matter, this metaphor works very well. On the micro side, particles are more disordered in the gaseous state than in the liquid state, and they are more disordered in the liquid state than in the solid state, which is what we observe on the macro side. The entropy of gases is higher than that of liquids, it's higher than that of solids. The image, the metaphor, works. On the other hand, for another equally important example, it does not work, even though it is of the same level of conceptual difficulty. Take 1 mole of each of the 4 first noble gases in 4 containers at the same temperature and volume. Indeed, a person who only works with the heuristic entropy equals disorder will probably think that the molecules of the 4 gases are disordered in the same way, and therefore that the entropies of the 4 gases are identical, which is not correct. In this case, the solution lies in another property, less known and less intuitive than disorder, which is that entropy depends on the mass of the atoms under consideration. This is a consequence of the model of the particle in the box. The mass of the particle influences the number of accessible energy states, and therefore the entropy. Consequently, the entropy of krypton, the heaviest, is greater than that of argon, neon, and helium. Now here I'm going to show a first result. When we give this question to a group of chemistry students in first year at university level, before a course in classical macroscopic thermodynamics, and the pretest is in blue, we can see that the majority of students choose the answer chooses the incorrect answer of the identical entropies. Worse, we observe that after the course in orange, the great majority choose this wrong option. What they were taught and the way it was done reinforced them in a misconception of entropy. So if the disorder metaphor does not work even for some simple cases like this one, so why do we use it? Well, it stems from the history of entropy, which has seen two methods for explaining thermodynamics. During the 19th century, Carnot, Clausius, and oh, sorry, there's two times Clausius here. He's supposed to say Gibbs. Sorry. Formed a classical theory, but not an atomist one. It functions without particles. It is a theory that is still presented in the majority of bachelor curricula. In 1877, Boltzmann proposed a statistical explanation of thermodynamics. By considering quantified interactions between particles, we can find the same quantities as the approach of Clausius and Gibbs. The metaphor of disorder is therefore alone a transfer from the statistical microscopic method to the macroscopic model. Once again, the macroscopic method does not require the use of particles, though it uses a metaphor that does. This borrowing is thus a symptom of the coexistence of these two theories, which raises some questions, such as, if one borrows, as with the metaphor of disorder, shouldn't it be well framed and its limit well defined? So the pedagogical framework of this research is the work of conceptual change, where a misconception is a naive, incomplete, or just plain false conception of a scientific concept, and the conceptual change theory, a framework for observing and analyzing the ways in which students' conceptions coexist and evolve. Basically, my research questions are, what are the misconceptions of first year and second year bachelor students at university about entropy and the second law of thermodynamics? And how do these misconceptions change after a macroscopic approach lecture? So the method I use, I administered a test with 11 questions, including the questions of the noble gases that you just encountered, to populations of bachelor students, including engineers, chemists, pharmacists, and geologists. The data you will see here are those of pharmacists, chemists, and geologists in year 1. The questions have been created to make misconceptions arise, to let us analyze them, and a test is administered once before and once after to see how the course has affected the misconceptions. Here is a result from one of the questions. On the left, you have the question that was asked. Entropy is with several items to choose from: a temperature, a form of energy, a thermodynamic quantity, etc. On the on the right, a graph showing the results of a population of about 100 pharmacist chemists in year 1 in pre-test. At this stage of the curriculum, the students have already had a course in general chemistry, which talks about entropy, and they have already made numerical calculations about them. In orange, you have the items which are the wrong answers, such as entropy is a process, which is wrong, and in green, the correct items, such as entropy is a thermodynamic quantity. Again, immediately notice 3 important results indicated with these arrows. With the red arrow here, you have the misconception that entropy is a form of energy. It's present at 48%. This is a lot, given the importance of the distinction between the two in a classical thermodynamics course. Of the qualitative answer obtained to justify these misconceptions, some spoke of the fact that entropy was a form of energy, as would be electrical energy or potential energy. Then, indicated with these blue arrows, we noted that only half the students select the correct items. Entropy is a system property, and entropy is a state function. These are therefore 2 characteristics of entropy that are not well known. We have analyzed textbooks and courses to try to understand this, and I suspect that this lack of knowledge is rooted in the fact that the macroscopic approach favors the process over the property. Teachers will talk about entropy variation in time and with a reaction, not entropy as such, which suggests that entropy is something that is attributable to an evolution, not a property. And let's see the evolution between the pre-test and the post-test after a classical thermodynamics course. The course has a positive effect on the energy item, a form of energy item, but still 1/3 of the students have an important misconception. One can suspect the misunderstanding of the fundamental formula ds is equal to dq reversible over t, which the students may interpret as an equality between heat and entropy, thus energy and entropy, but we still need to pursue reflection in future semi-directed interviews with students. The thermodynamic quantity and state function items are improving, and they are precisely very important in the macroscopic approach. And the course seems to have a negative effect on the property item, which, as I just explained, is not an aspect that is strongly emphasized in a classical thermodynamics course. For example, we will ask in an exercise to calculate the difference between the entropy of the reagents and the products to predict whether the reaction is spontaneous or not. We will not ask what is the entropy of the products and that of the reagents. So what should you remember of this presentation? First, there is a major conflict between macroscopic and microscopic approaches. Often, chemistry students are introduced to the macroscopic method first, with what I qualify an unjustified borrowing from the microscopic method, and then they study the latter in a later course in statistical physics. The poor collaboration between the two models, the bad mixing, is identified as a source of misconceptions. Our results show that a classical macroscopic thermodynamics course does not necessarily improve misconceptions. And the next step in our study will include a better joint explanation of the two models, perhaps by improving the metaphor of disorder, such as adding the notion of movement quantity disorder, which is often forgotten, or by better limiting its use and relevance, or perhaps by proposing new methods of explanation, which could include putting the statistical method first, then the macroscopic method. From there, we will construct a new didactic approach to entropy, which will also make use of pedagogical devices that can more easily implement these new ways of explaining entropy. I see that it was a bit short, but I'm really glad that we have more time for questions. Thank you for your attentions. I hope this has given you something to think to, and I look forward to hearing your feedback.
Thanks a lot, Vincent. Very interesting study indeed. And I suppose, it gives a lot of thought about actually the sources of misconceptions and how these actually continue existing within the student's mind as they progress, if you like, even at undergraduate and perhaps postgraduate level. So thank you very much. I'll just open the floor here for questions. You can either type in the question in the chat box here, or if you prefer to turn your microphone on and ask, go on. We have about 7 minutes for questions. So
if nobody else wants to go first, So first of all, really interesting talk. I appreciated that a lot because I had a similar revelation about teaching entropy a few years ago when I went to a talk by a physicist I mentioned in the chat. One thing I just wanted to ask was, I think you correctly identify a couple of the sources of these misconceptions here, like mixing the macroscopic and the microscopic model. One thing I wanted to ask was, have you thought of, because one thing I find is that students don't find it hard to appreciate what entropy is because it feels like a sort of magical thing that only relates to, equations off in the distance, whereas we have a kind of an everyday understanding of what energy is, or at least some understanding. Yeah. But entropy is another thing. So an example I like to use is, I actually have my props here because I was giving a tutorial the other day, is just to use a couple of macroscopic things like a normal ballpoint pen and one with 4 modes on, and say this one has 2 degrees of freedom on or off, whereas this one has 5 different choices off all the 4 colors, and therefore this has a higher intrinsic state of entropy than this by that definition. So have you got any examples of that nature?
Yes, actually, we think that the approach of degrees of freedom could be one of the solution, like how to explain why rotation, degrees of freedom, vibration, and translation and how these levels change with respect to external factors. How, like, for example, increasing the pressure changes these energy levels, and how these energy levels give rise to entropy, or how entropy defines them. And I want to say too that there is between, I totally agree that energy seems intuitive and entropy does not at all. And I think there is something to do to, I didn't talk about it, that energy is conserved. As many laws in physics, it's a conservation law, but entropy always increases, which is, I don't know any other laws that says in the universe this thing always increases, which is, in my opinion, a source of misconception for students.
I agree. I mean, one thing I occasionally bring up, even though it's more of a physics thing that doesn't really impact on us directly, but for that one, I like to say that the way some physicists approach it is, rather than saying, why does entropy always increase, to say, how do we define time is going forwards, not back? And we say time, the arrow of time points in the direction of entropy going up, which is just more of a thought-provoking point. But, you know, that way it makes it sound a bit less arbitrary than it just keeps going up because reasons.
Yeah, totally.
Thank you.
Thank you.
Thanks, Addison. Any other questions from the audience here? If not, perhaps I could go for a question, Vincent, if that's okay.
Oh yeah, sure.
Yeah, I don't see any other questions in the public chat box. So yeah, very interesting topic. And you know what I like more about your presentation and the way you're doing it's about that conflict, if you like, between the microscopic and the macroscopic level of understanding. Which I suppose, you know, that reminds me of these famous talks of Feynman, where he was actually saying, you know, it doesn't really matter. I mean, you know, what sort of explanation do you want? Do you want actually the microscopic one? Do you want the microscopic one? And that's, if you like, what can guide, if you like, the answer you get and how much of it you can understand. So perhaps, you know, that may not be reflected in your study, but I would like to hear your view of that. To what extent do you think, you know, it will be easy for students to be holding, if you like, a dual way of reasoning? So when you ask them about phenomena that the macroscopic level understanding is required, they can get actually a really solid and good understanding. And when they need the macroscopic, they can switch into that, if you like, and go for that sort of reasoning.
Yeah. I think I have no clear answers from the literature to this, or I just have my personal opinion, but it is something that we work on, and I only showed you 1 or 2 questions, but there are 11 of them, so there are very interesting things that can come up from this. I think that the coexistence might not be the solution to diminish the misconceptions. I think maybe the solution is putting the microscopic method first. And I think we've kept the macroscopic method as the first line because it seems more easy, like you have simple equations, you don't have a lot of things to deal with, but it does not explain the phenomenon. It's more a descriptive model that says, well, there's something called enthalpy, there's something called entropy, and that's it. Whereas if you start with a microscopic approach, you can pose some more acceptable axioms like they are particles, they are indistinguishable, and they interact in this way or this way. And then you build the macroscopic method from the microscopic method. As for now, it's my opinion, and it might change with the results of the student. But I think this might be the way to go.
Absolutely, and I would agree with that. You know, from my experience teaching, if you like, physics, is, you know, the two, if you like, levels of understanding, microscopic or macroscopic, are not incompatible. So it's about, you know, which one you introduce first, perhaps, and how you build the one onto the other to get, if you like, a more holistic, if you like, understanding of the phenomena, whether you're looking at a microscopic or a microscopic level. Vincent, thank you so much. Really interesting study. I'm conscious of time, so we need, I think, to move to the next presenter. We have Anne Mudve.